Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So anyway, thanks a lot. We are repeating this. I think last time I came, there were only a couple of people, and both were my interns. So I think we're rescheduling it. So probably good to see better audience. All right, it's not showing up on the projector. I think now it is. Okay. All right. So, so this is a talk that I have combined, multiple works, and so when I started thinking about, machine, so specifically the problem that we'll be looking at is, some recognition problems in machine vision, like, face recognition, things like those. And I mean, I take the perspective that context can help a lot in some of those machine vision tasks, and specifically people have not really been looking at context a lot. And this whole project or lines of projects have been trying to exploit, whatever can we do beyond just trying to, do high-level processing at the pixels or trying to find more richer features, right? How can we just exploit the context? So again, like context can mean a lot of different things to people. So when I first announced this talk, like some folks from sensor network groups came to me, and when I spoke to them, the context meant something that I wasn't really thinking about at that time, right? So for this talk specifically, I'm really interested in recognition, in classification specifically, and the contexts are all those cues that can help me boost recognition, right? So for instance, as we'll see, right, we are going to mainly focus on, image recognition problem, and specifically face recognition. So identities of the person, right? So, of course, I can process each individual face, and I can recover whatever informative feature that I think works best. Like, for instance, the shape of the eyes, aspect ratio of the face, even the skin color, right? And that's more towards feature engineering, right? But on the other hand, there is a lot of other contexts that we can exploit. So things like, who do you most often appear with in a photograph, right? Where was this photograph taken? What time of the day, right? What's the background looking like? So there's all of these things which are not specifically trying to engineer features, but trying to exploit, the co-occurrences of events, places, things like those, right? And so that's the setting that we're going to work on. We're going to sort of, go through 3 or 4 graphical models, which tries to incorporate different kinds of information, right? And so again, this is just situating the problem in the setting of face recognition, but you can imagine trying to do similar recognition tasks in other domain, where there might be other variables of interest that can inform your final classification task, right? And as I said, we are interested in people, right? So one simple thing you can use as co-occurrences, right? If I am, like if there's a photograph in which the image recognition algorithm can very well detect presence of my wife, right? It's likely that the other person is me, like in, say 70 or 80% of the cases, right?
This is hopeful, right?
That's hopeful, yeah. But again, it's the statistics, as you will see, like we are not going to hard code it, right? And similarly, you have events, right? People go to parties, they collect a number of photographs. So, it's a burstiness nature, right? It's like none of these photographs actually, kind of independent. They are, governed by an event that occurred clustered in time, right? And also then people are clustered, right? If it's an MSR wind down going on, then you kind of know that most of the people are going to be within from MSR, right? And of course, you have locations if you have additional informations like GPS information, etc., right? So let's try to think about how people have tried to use context, like most of the time, right? So usually, people would try to use context as a feature. So imagine if I have a classifier that can detect location, or a classifier that can detect event, then I can take the output of that classifier, right? use that output as a feature, right? And then I can train basically a higher level classifier. But the problem then there is that, it kind of depends upon the quality of your underlying classifiers, right? So if my location classifier is not any good, it's not going to help me, right? And similarly, others, right? So here, right, and of course there have been other methods that hard code the relationships of different like phenomena being happening, and then try to exploit that relationship, right? But there is one of the things that sort of drove us in this work is that instead of assuming an existence of primary task, which is such as face recognition, and secondary tasks such as location and event detection, instead what we can do is we can instead flatten this. We can actually use bootstrapping capability from each other. So in a nutshell, if I know the persons in the photograph, and if I know the locations, then probably I can guess the events. Similarly, if I know events, if I know like where it occurred, I can sort of guess who the people are, and you can actually, this kind of combination and works in any possible way you'd like, right? And that's what we're trying to achieve. What we're trying to do is basically help these classifiers bootstrap off each other, right? So instead of trying to train them independently and then sort of cascading that output into a high level classifier, we'll try to basically train them simultaneously, and so that they can bootstrap off each other, right? And to do that, we'll actually use graphical models, right? And some of the things, as I said, what we can use is we can use clothes, right? For instance, what clothes people are wearing, right? You can have a clothing feature or a clothing detector, timestamps, right? And people have used such things in the past, but again, these are nothing but features that go in. So it really assumes that you have a very well performing context detector, right? So let's try to build one thing at a time, right? So first, I'm going to use a very simple model, right? So let's first think about constraints that are induced in a photograph, right? So if I have a bunch of photographic collections, right? So the first thing that I get from my prior knowledge is that if there are two faces that are appearing in the same photograph, they need to be of different people, right? So that's one kind of context, right? That's very simple, right? Similarly, if it's a video and I've been tracking a face, right, I can kind of see that probably it's the same guy, right? So it's a very simple constraints, and we are not adding any kind of people, location, event thing yet, right? It's a very simple, right, this constraint. And how can we actually exploit it, right? So first I'm going to show you a graphical model that just tries to model these constraints, and on top of it we'll add the other modalities, right? So, well, this is the graphical model, but I'm going to explain it to you one thing at a time, right? So, all right, so let's start from the top. Let's basically let's assume that this is all covered, right? Just the top portion, right? So y1 through yn are imagine the true IDs of n different face patches that you have observed, right? So if in a corpus you had 100 photographs, and out of that you exclude you basically extracted say 500 face patches. So 1 through 500, y1 through yn is basically nothing but the true IDs, right? And basically what I am showing on top is a potential function which is encoding a Gaussian process prior. But again, let's not get into the details. But what you can think is that suppose if you had a classifier that would take in x's, which is the image patches, right? And it would output the IDs y1 through yn, right? So basically the first half is nothing but a classifier, right? The second half is that you are observing, right? If it is a shaded node, you basically say that that's observed. So what you are saying is someone has given you the identities of T1 and T9, which is some face ID, right? And the rest you need to infer, right? And then what you have is you have these constraints that are coming from your prior knowledge, right? So if two images came into the same, photograph, they are, represented using these red lines, which is basically saying that, T7 and T9 cannot be the same ID, T9 and T8 cannot be the same ID, and similarly here. Whereas a green edge would say that these all needs to be the same ID, right? So intuitively, right, there are two parts. So the first part is a simple classifier that you have trained using any feature-based method, computer vision, right? But on the other hand, you have these constraints that are coming out, right? So so this is basically the graphical model, right? So again, if you're interested, these are the exact form of the potential functions. But in the end, what I'm going to do is I'm going to just do a message passing, right? And all of these things are hidden variables, right? And once I do the message passing, I should have probability distribution over everything that's unobserved, right? So essentially, intuitively, your message passing is going to do the following. It's going to first classify, right? So that's all of these guys, right? Once it's classified, it's going to look at, these constraints, right? And it's going to resolve the constraints. So since all of these are probability distributions, right? You can basically use these constraints to further, refine your beliefs in the final, labels, right? So intuitively, first you classify, and then you resolve the constraints. That will result in new labels, right? And I can actually use these labels again to further retrain my classifier, right? And you can keep doing this thing on and on till it converges. And basically what essentially I have told you is a variational message passing algorithm, where the first hidden variables are basically inferred using a classifier. Then you run some kind of message passing at this layer in order to resolve the constraints, right? And then you again pass the messages back so that you'll refine these guys again, right? So that's what's really happening. Yeah, Misha?
Are you assuming the number of classes is known? And for each class you have training examples? Or?
Well, the thing is, the way we've implemented it, we don't assume that, right? And again, it really falls through from the structure of the Gaussian processes. Really, if it's basically, the structure is your classifier is of the form that, you have a matrix times the labels. And these labels are nothing but indicator matrices, right? So if you have more, basically if you have more classes coming on, all you need to do is just append your label matrix. And so, again, I'm skipping a lot of details, but, it's kind of, that's how we implemented it.
There's really a step over the number of classes, right? Also in the real
So, yeah, so again, here's the thing. So for one inference step, we assume that we know the labels, right? But you'll see that we're going to do a little bit of active learning on top, and that's where, you don't need to really, you can break those boundaries there, right? All right, so clear, right? The simple message passing, right? It's first classify, down, resolve the constraints. And the way you resolve the constraints is basically simply loopy belief propagation here, right? And then pass the messages back. Keep doing it till it converges, right? And right, I'm yeah.
Can you show convergence?
Well, the thing is, if it weren't for a loopy belief propagation, you could show the convergence, right? Otherwise, assume that you can do this constraint, this step, perfectly, the constraint resolution step. The rest of it is just simple variational message passing, which is it's going to go to a local optimum. But because of existence of loopy belief propagation, you cannot guarantee it. But in this application, the graphs are such that the loops are fairly less. So, it's not a problem, but, right? All right, this is the details, we don't need to go over it, right? All right, so,
Yeah. There's been a bunch of people who've done this kind of layering classifiers. So you have a classifier at phase one, and then you kind of train given the set of classifiers you have at stage two.
Yeah.
And so you basically are kind of stacking classifiers on top of one another. And this is similar in some ways because this has this, you're going to take the information given the first classifier and then kind of adapt to it.
Yeah, but also the thing is, you need to notice that the information flow is both ways, right? So classify classifiers, and then based on those potentials, you have your constraints and you resolve those, and the messages then get passed back, and so it refines the base level classifier as well. So
you can unfold the temporal evolution of those things. So you can think about it as stage-wise. So you have a classifier trained, and then you kind of have the update via the second layer, and then you get the new update. So
it's basically it's an unfolding happening. You're right. I mean it's a similar spirit, right?
And so what's different in that work is that they're doing it for a set of classifiers here, and so I think they're combining different information. Combining different information.
Again, I'll have to look at the paper that you're exactly talking about. But I think in philosophy, like in a sense, the idea is very similar. That you have multiple classifiers, they all can inform each other, right? So instead of doing piecewise linear, right, you can do is try to basically do this graphical model way in which you have a message passing way of training all the classifiers simultaneously, right?
You're not exactly training them simultaneously, right? You do it in iteration, right?
Yeah, you're doing iteration, right? And in ideal world, you should be able to do.
It's not as if you do gradient descent on all of that kind of.
Well, it's a kind of gradient descent. Like you can view this as doing a coordinate ascent, where you kind of clubbing some set of variables.
More similar to kind of the remote ascent like that you fix one, and then optimize.
So instead of fixing one variable, you're fixing a group of variables. Yeah. You can think like that also.
Kind of alternation.
Right? It's alternation. And again, if in real world, right, I would be able to do this inference exactly, right? Imagine if I have a huge sampling capability. Essentially what I'm saying is what I'm limited right now is by my inference procedure. If there were a way to do exact inference, this would be as if I were doing it simultaneously, right? So one is the model, and the other part is doing the inference. The inference, because of the computational reason, I'm using it variational approximate inference, and which has the flavor of doing iteration. But had magically, I had a capability of doing exact inference, then in essence I would be training this, simultaneously, right?
Another question. So you have here the assumption that the prior is normal, which is
this is basically there is a very good correspondence between this prior and the regularizer that's used in SVM. It's essentially the same thing.
How strong does it depend on that? So if the prior, do you have some way to control? What if the case that this is the wrong prior? How bad can it be, or do you have any?
So let me try to answer this question in a different manner. Imagine there are no constraints here. Imagine there is nothing here, right? Then this model is same as regularized least squares. Basically, it's essentially right. So then it boils down to the question: how good is regularized least square, right? So again, so you need to make sure that your features are appropriate, right? All right. So again, let's move over it, right? So now the good thing about this is like fully Bayesian inference going on. So I can do things like active learning using value of information computations basically. So what I can do is I can ask questions like, so given T1 and T9, I have a posterior distribution over the rest of the label set, right? So I can ask that, hey, if I knew T8, how is this posterior going to shrink, right? So now you can imagine that if I knew T8, I would automatically know what T7 is, right? Because of the green lines. But if I knew Tn, then it does not give me that much information, right? So I can do this kind of sort of reasoning in order to guide my active learning, right? So imagine now that if I have like hundreds of photographs, but I have a really long video sequence, so it makes more sense for me to get a label for a single frame on that video sequence in order to have a lot of discriminatory information that I can use to train classifier. So so this is the first sets of experiments basically that shows how well it works with active learning. Again, I mean, you can get this results, in the paper, but basically, as you get more and more labels set, you tend to do more. The blue line here in all of these graphs, so they are like 4 different data sets. The blue line is if you don't have any constrained resolution, you're basically training as if you had a supervised classifier, right? And the rest are, once you have, right? So yeah, once you have the constraints, then how well you do, basically. Again, you can results as you can read. And all right, so moving on, right? Now comes the more interesting bit, where so far, we were only talking about this modality, right? So from image patches, right, figure out the identities, and then you have these constraints in real world, right? But now imagine you had like other classifiers as well. I have a location classifier, I had event classifiers. For people classifier, I was just looking at the image patches, right? But for characterizing a location, maybe I can use the background. So from the images, I can compute a simple feature that looks at the histogram of the background, right? Similarly for the event, if I have the EXIF data from the file, I can just look at the timestamps, right? And maybe even GPS coordinates. But so some features that you can use. So if there were no connections like these, then they would be like individual classifiers, right? Which basically looks at the background scene and then tries to guess what location it is. Similarly, like it looks at the timestamps and tries to classify what, right? But now I'm going to put this links, and this is where the message passing is going to happen again, right? So as I said, if I knew who all in the photograph were, and I can characterize the location, then it gives me a lot of information about the event. Similarly, if I know what event what is and what location was it, then I can get information about the people and all all possible combinations such as those, right? So let's look at how do we do that, right? So the crucial links are these guys, right? And in the beginning, I also mentioned that the fact that co-occurrences of people can also help you, right? And so that's what's shown by this self loop, basically. And let's try to see how do we model these links, right? So I'm going to model these links using basically a relational table, right? It's nothing but a table, right? And all it encompasses is the statistics of people and events and when they are occurring, right? So basically an entry 0 says that this guy is probably not present at an event characterized by these group of pictures. I mean, it's a group of pictures that I have used to denote an event. But what all this table is capturing is the likelihood of all these people present in an event. I wouldn't even say likelihood, it's a compatibility function basically. So when it's 0, these guys are not likely to occur in this event, but these guys are, right? And yeah.
You're defining event as just some arbitrary group of pictures, or?
Well, the way we defined it is clustering in time. So we run basically a clustering on the timestamps, and we say that these guys are different events. That's how we are defining it, right? So, and similarly here as well, right? So basically, this is all unknown to us, but right now I have filled those entries just to, explain things, right? But if we had a table like these, this information can be very useful, and this is what we will use in order to do our message passing, right? So this is nothing but a compatibility matrix, if you'd like to think of it, right? How compatible are certain people in certain events, which is encoding, likelihood of their presence, right? And yeah, right, basically who they are and where, right? So let's just work with 2 domains right now for simplicity. So we had the people domain, right, where we are looking at face features and cloth features, and we could just simply classify them, right, as we did it in the previous thing, right? And similarly in the event domain, we have timestamps, and we can just simply classify, right? But now we want to sort of do a message passing, and that's where the relational model sits, right? So again, it's just nothing but a simple compatibility function, which is nothing but a 2D table. Again, the entries are not known to us, right? But if you knew entries to us, if you know those entries, then I can again simply do the message passing as I did in the earlier slide, right? I classify these guys, I classify these guys, I look at the relational model, and I basically try to resolve the constraints, right? And then pass the messages back and keep doing it till it converges, right? Of course, the problem is I don't know what this relation model is, right? And what we're going to do is we're going to actually learn that as well, right? And again, in terms of probability formulations, if you're interested in the formulas, I can go into the detail, but it has only 3 terms. The first 2 terms are the unary potentials, which are nothing but the unary classifiers. So basically these guys from here to here, here to here. So what is the likelihood that if I observe a certain facial features and clothes features, that the ID of the person is something, right? And the second term is nothing but the compatibility. This term is nothing but the compatibility across 2 domains, right? And again, we can go into the details, but I'll probably keep it at very high level. As I said, classify this, pass the message along if you know what this guy is, right? And so the way we are going to do it is basically EM, right? And again, use the parameters of these guys as a, think of them as a theta, right, a variable. So in an EM step, right, you have an E step where you first figure out, you basically classify these guys, right, and given your theta, you can compute the likelihood of the model, right? And then what you can do is you can try to optimize that with respect to this guy. So in a nutshell, right, what's really is happening is you first infer a distribution of the label given some initial value of theta, which can be uniform, right? And then once you have that, you can try to maximize the model likelihood, over your thetas, and you can just keep doing it. So it's variational inference, but on top of it is an EM step going on, right? And basically, what to the algorithm all you gives is a bunch of images, a bunch of face patches, and it automatically not only just classifies them, but also finds out the relevant relationships, right? So by just using this graphical model, what you have really done is you have provided a structure, and you are exploiting that structure in order to recover the variables of interest, right? So in a nutshell, right, it's a very simple model. Classify these guys, given this thing, find the likelihood of the model, and then optimize with respect to this guy to maximize it, and keep doing it, right?
So, it's not clear to me where the relational model is coming from. So in this example, you said, you have these red and the white, so the zeros and the non-zeros in this matrix.
Yeah.
So, and you drew it so that that's the structure that you have in that graph.
Yeah.
Where did that come from?
So, well, that's the thing, right? So this is unknown to us, right? So that's the parameter that you need to find out as well, right? And that's what the EM step is doing.
There's a structural element to it.
Yeah.
So the structural is the red versus the white.
Yeah.
And then there's the parametric part of it. And so, are you also identifying the structure? What it wasn't clear to me is whether you
the structure is fixed.
Well.
So structure is fixed.
So how do you get the structure, the red versus the white?
Oh, so structure is very simple, right? So this is nothing but a giant table. It's a lookup table, right? So in graphical model terms, right, this is a random variable, then this is a random variable. An entry here basically tells you the compatibility of this value of the random variable with this, right? So it's basically a simple 2D parameterization, right? And that's where it's fixed. Yeah, everything is numbered.
So it's not red versus white.
No.
So you don't have any structural information.
Nope.
So the graph in that second picture is misleading in the sense that you have edges going from every person to every event.
Oh no, yeah, we do actually have it. So it's one way to think about it is the following, right? So this is one random variable, right? The rows represent one random variable. The columns represent one random variable corresponding to each face patch. Correct? Right? So then basically this is nothing but a potential function between this guy, this random variable, and this random variable, right? And yeah, so that's pretty much it.
So do you assume that this table contains any additional information that's given you from the outside world, or is it something that you extract yourself?
Yeah, that's something we'll extract ourselves. So this table is unknown to us, right? It's unknown.
If someone tells you, look, in this
Yeah.
picture, it's
Yeah.
either this
Yeah.
either
Yeah.
Joe or
Exactly.
Jeff is in the picture. I don't know who, but one of them is in the
So here's a hypothetical way to learn this table, right? So I have, say, unary classifiers that classify people just based on the patch and location just based on those things, right?
You're using probabilistic classifiers.
Well, this is, yeah, probabilistic classifier, but let's assume that they're just, any SVM or anything that you have, right? Then what I can do is I can just look at the output of those classifiers and then roughly come up with this table, right? And as long as those classifiers are a little informative, so that they are not completely random, I'll have some reasonable, estimate here, right?
What I don't understand
Yeah.
is that this doesn't add any information.
The information is coming in terms of structure. That's what I'm trying to say, right?
So
What I have encoded in the model is the fact that certain people tend to, basically tend to be present at certain events, but at certain events they are not, right? I mean, that's what I'm saying using this. Like there is a.
I'm trying to understand
Yeah.
what you said.
Yeah.
So in the table itself, if it was just extracting this data, there is no additional information.
Yeah, exactly, right.
So the additional information comes from the fact that you say
I'm imposing the fact on the learning
some
model.
prior
Yeah.
over these tables saying that, for example, these two guys, they tend to appear together.
Yeah.
Or something like that. Okay. So,
Yeah.
so the structure is the additional information is not in this table, but something on kind of.
So here's the thing, right? Suppose if I were just, training independent classifiers, right? What's the difference between this model and that, right? The only difference is these links. So by explicitly specifying this dependency, I have added information.
So in other words, just because two pictures appeared at roughly the same time,
Yeah.
you're now biasing.
Yeah. I mean, that's constraints that you're adding. Exactly. Yeah.
You mentioned something like, for example, it cannot be the same person in the in
the same
picture.
image, yeah.
So, for example, you also seem like you want to encourage the same people appearing in the same one. What are the specific templates for these things that instantiate the prior? Because the prior comes from these templates. There's some model that.
All right. So So one is, when we talk about prior, I think, the way I'm thinking about prior is probably a little bit slightly different than how you're thinking about the prior, right? So let's start from very scratch, right? If I have just unary classifiers, just looks at the faces and then classifies them, right? And right, that's a simple classifier, right? There is, and it can be SVM, it can be logistic regression, it can be decision trees, whatever it can be, right? Similarly, here I can have another classifier, right? So, now, what I'm going to say is that the output that I observe here are not only dependent upon this, but also going to be dependent on the output of this guy. I'm explicitly encoding in my model, and that's the extra information, right? And there's no other extra information. I'm not specifically hand coding any kind of statistics or anything.
So that's an initial version of the matrix that it just said that I found Joe in this
so
event and so on.
if you knew this model, right? If you knew this model, it basically just tells you how to marry these two labels. Like this is just a compatibility function, right? It's all it's saying is how do I make sense of when I observe things here and things here, right? When it's absent, there is no way for information exchange, right? So you basically say that all right, whatever my classifier is given is fine.
The structure, right? So it'll say that there's the same label cannot be in the same picture.
Yeah.
If Joe appears in an event, at least one of the
exactly,
right.
right.
event must be Joe. And
So that's
what are these templates? So what are the actual potentials that you're instantiating?
So there are 4 different kinds of potentials, and so basically one is people event. So you have a one face patch, and you have random variable corresponding to the event that image was taken in. So there's a compatibility function there. Similarly, between event and a location, and again location and a people, and then a people and people, right? So all those 4 links. So you have 4 different compatibility tables. But again, this is going into the details. Assume that if I just had only 2 domains, let's not even worry about the specific application. If I just only had 2 domains, right? if I had simple classifier, there's no way of exchanging information unless in my model I explicitly spell out the dependency, right? And this dependency is through this relational model, which is parameterized, right? So if you know, then you know how to sort of marry those two domains, right? So that's okay.
So this matrix is not per image, but per group of images that the timestamp classifier told you these are
not even group.
Images
every face patch. So every face patch is a. So you have a face ID, right? And you have an event ID corresponding to every face patch, right?
But event ID is you're gonna have multiple pictures.
Yeah.
With the same event ID.
Yeah.
This is where you.
Yeah, exactly.
This is where the.
Yeah, this is where. Yeah, so those parameters are shared across. Yeah.
Because if you didn't have this information, then there's
these parameters are all shared across. All the institutions. Yeah.
Can you go back to the table?
Yeah.
She has 0.9 probability of being the event, the first event.
Yeah. So
what does that exactly mean? Did you learn this? Like, it should mean one.
So let's not worry about the learning. If suppose this is the table that someone has given you, someone has just hand coded, right, from prior knowledge. He basically looked at the invitation list of different events, like someone went in and he hand coded this table and gave it to you to the model, right? So this is how it would look like, right? So basically this table is saying that this woman with a very high likelihood will be present in this event, right? So if I detect, this event, right, then the chances that, this woman is of this ID is very high. That's all it's saying, right?
In any picture of that event.
Yeah, in any picture of that event, yeah. It's basically compatible.
It's equality for that potential for all pictures in that event. You're saying. If she's in multiple pictures, is that more likely then?
So, again, let's.
And you ignore the face patch. It's like whatever face patch it is.
It's that. It's just
So it's a pooling template. So it's pooling over all the.
It's basically it's saying again it's not looking at the features at all. It's just looking at the random variables on top, right? And it's trying to basically it's a compatibility function, right? It's a way of saying that I am going to be present at this event, right?
I'm trying to understand what the number 0.9 means. So does it mean that
it's not a probability? It's some number. It's a function. So the thing is, this is an undirected graphical model. So if this number is high, it basically says that the likelihood of this person is high.
Right.
Yeah.
If it's 0,
yeah,
right,
that means completely not.
That phrase should not appear.
Yeah, exactly.
If it's 1, does it mean that
no,
it
it
has
does
to
not
appear on every
No,
image?
it does not. It does not.
It does mean that it has to.
Well, if it goes to infinity, but we don't. That's
infinity is the scale. So at infinity, it means it has to.
But it has to appear. Does it has to appear in the event, or does it have to appear in every image of the event?
What it's saying is that if it does not tell about every image, all it's saying that if an image is clicked at a certain event, right, then if if it goes to infinity, then it will basically theoretically say that that person should be present there.
In every image.
Yeah.
It's not that it's present in the event; it's
present in the image. Yeah, right. And again, these are unnormalized. 0 means definitely what you said, but
So it goes from 0 to
So it's every image. So it's not pooling across all images and saying if there's at least one where they're present. It's actually penalizing for lack of presence in every one.
You estimate it's pooled.
Yeah. So when you estimate, that's how you'll pool it. That's when you pool it. But if I'm just given this function, right? It's basically telling me that this is the compatibility between these two random variables. That's all it's saying. It does not tell me about whether it's like certain or not, because it's not giving me a scale, right?
Like you're saying, if it's the maximum value,
then but
across all the
but this is unbounded, right? This function can have any real value actually. It can also go negative. Like we didn't implement it that way, but it could actually go negative, right? And right, so again, this is all of this thing actually gets resolved when you compute the partition function. But let's not go there. But again, if someone has given you, then that's how you need to interpret it. The question is we don't even know what it is, right, to start with, right? So the
Image, you can use the thing on the left to say here are the people in it.
yeah.
You can use the thing on the right
Yeah.
to say this is what event it was.
And then
based on that matrix, you
and
say
then make a
consistent.
exactly. That's what is going to happen, right? The way we're going to learn, right? Learn those parameters is first you classify these things individually, then count, come up with that table. Once you have that table, you can further refine it back, these guys as well, right? And then keep doing it. Again, it's an EM kind of thing. Yeah.
So in that EM framework, where do the constraints get implemented? Are you solving a constrained optimization in the step? Is that where you put them in, or is there?
Well, E step is basically, again, we are doing it very simply. So the way actually it is implemented is first, all right. So first fix this guy. So first all right, classify, and then estimate whatever it is, right? Then fix this guy and this guy, and then sort of redo this thing. Then fix this, and then redo this, and then redo this, and then you keep doing this, right?
Like a joint optimization framework, you're actually doing all
it's a coordinate descent.
between
Yeah.
So you're guaranteed to kind of converge to the
into a local minimum. Yeah, it's a variational message passing.
It's already
Exactly. It's basically a variational algorithm, right? It's same flavor as doing clustering, mixture of Gaussians, right? Exactly the same thing, right? And these are the details of it. And again, I think as I said, it's basically an iterative way. We can basically look at some of the results, right? So if I was just using simple face classifier, right, just image features, I can do well, there are two different data sets. I can do up till say 39%, right? That's the best. It's basically it's state of the art. This is the MSRA face recognition library. So we collaborated with the Bing folks on this. And pretty much, this is like around 30, 40 class problem. It's a pretty big, right? So the marginal is less than 1%, right? So even state of the art on a very hard image recognition tasks is, not more than 30, 40% actually, right? And it's, and this is like real, these are Facebook data sets. So there's all weird kind of poses and all that thing, right? So, yeah, so I think this is, 15 classes. Sorry, this was like 30 classes was the earlier one. This is a 13 class problem. And yeah, this is pretty much state of the art. This is, the best they could do on this data set using, number of different algorithms. So Simon Baker and Amir Akbarzadeh, they are like face recognition gurus, essentially, right? So next, what if we start to incorporate the statistics of co-occurrences of people, right? So it goes up a little bit. Not that much. Still, it's a hard problem, and co-occurrences, you can imagine that, are limiting. But as soon as you start incorporating events and events and combine these two, it shoots up pretty much to 95%, right? And if you imagine, it's a 13 class problem, right? But if it's, if you go to different events with say group of 2 or 3. Suddenly knowing an event reduces your 15 class problem to a 2 or 3 class problem, and that's a big, that's a big information you can actually exploit, right?
Do you have any sense in how it decays when you have a much larger class? 20 isn't that. If I look at my photo album, 20 is not very big.
Very big, yeah.
Right. And so, do you have any sense how it decays?
Yeah. So that's something that we are actually now looking at, especially looking at like large corpus of this is preliminary studies, but our sense is that more the classes, the better the gain is. Just because if I can reduce a 300 class problem to a 5 class problem, it's better than doing from 15 class problem to a 3 class problem, right? So it's a
better the relative gain, whether or not
better the relative gain.
Useful is the question.
So better the relative gain, and it's in terms of it's a much harder problem to do a 300 class problem, right? So, that's a little bit harder to compare, but that's the initial sense. Again, I don't have concrete numbers on it yet. So,
tag.
Well, at this level, I don't even think automatic. You could make a great UI to say, it's this person, it's this person, it's this person, and it'd be really easy. But when you have 200 people, now is it still going to be useful or not? To be able to create a useful UI for labeling.
So for that, it would be nice to get the perplexities.
Perplexities,
Perplexities.
So
on a large vocabulary.
So the thing is, we looked at number of different Facebook data sets, and usually the order of different identities that people have really goes beyond 40 or 50 actually. The 300 is a really rare data set actually. I mean, I don't know, like my personal albums, if it's even of 300 identities, probably some of those faces are occurring only once or twice. And
they only occur once or twice, but that's a different problem.
Different problem, yeah. So that's a different scale of kind of problem.
One thing that's interesting about the UI, you're thinking of like an already an application for this. So in these photo album things, the easy part is to point out the mistakes of the machine, and the hard part is to correct them. So to look through your list of 300 people for the right match is the time-consuming thing. But it seems that here, you can just point to mistakes. You can just say,
wrong.
It's not what this is wrong.
Yeah, and then constraint comes in.
Because the constraints would come in and it would redo the index. So that would be a very useful type of feedback. So that's actually pretty awesome.
Basically, well, those red lines that we're talking about, right? Basically, it gets instantiated and you can do a message passing. That's great,
They actually have that in the Windows Live photo. I don't think they do a good job of using it within an event. I think that combining the red lines that you're talking about with the events, the event clustering.
So you just point at the mistakes. You don't have to correct them.
You can optionally point at the corrections or the mistakes.
Or the mistakes, So
these guys are right, these guys are wrong. It's actually pretty reasonable. It plugs in nicely to this.
So I mean, they are trying to put this onto an iPhone so that you can do some of these UI kind of things. I mean, the problem is not just machine learning. I think there's a lot of usability issues and all that. So I think they're trying to work it out.
It already has these types of input feedback, and so they can take this, I think, and do a really great job with it.
Figure.
This one?
The difference between only P and people to people. When you look at the right-hand side, you actually have more. So you added that relationship in, and you got more increase on the second, on the right-hand side. Do you have any idea for that?
So you mean so this jump is more, but not this much?
The delta between only P and PP.
Yeah, I mean, I think it's really hard to figure out how much the distance, I mean, that's something probably we should look at, but I mean, I don't have a good answer, but I think it's an interesting observation, I would say.
What is the size of the data set? How much?
Like 500 images, so this one is 500 images, this one. So 500 instances of, 13 classes. So event are more on this one actually, there are further more events. So again, these are, standard Facebook data sets. Basically a couple of people, Bing, who had they basically downloaded the album up, and that's how it is. So
the data eventually, when you measure correctness here, it's going to in the clustering sense, right? Did you?
No, it's an ID sense, exact classification. So
what is a label?
So label is the ID of the person, the image patch. That's what we're looking at right now. So each image patch has an ID associated with it, right? And our goal is to do the classification in that sense. Find the.
But then you have to have another data set in which you have some images of this person with the right ID. Otherwise.
Exactly right. That's how we do it, right? I mean, it's out of these, there are some instances that are seeded with label data, and then
how many are seeded and how many?
I think it's 40, 60, but I need to go back. I mean, I didn't put it up here, but it's something like that around, right? So there are some of them which are used as training data. So it's in a sense semi-supervised, if you'd like to think, right? You have a corpus of data, and few of them are labeled, but not of all of them, and then you do all this, message passing in order to. Right?
But then there could be, some of the reasons for this kind of difference in that you see, there is a big difference if you say 40%, but in every event I have a labeled image, then it's relatively easy, right? Whereas if I have events,
not necessarily. I mean,
missing events, then it's harder. It doesn't mean that it's trivial, right? It don't mean that it's trivial, but it's definitely easier if for every event I have an image which is.
Well, I don't know actually. The thing is, if you look at this diagram again, these guys are pretty independent. When I'm training these classifiers, these features, right? The only relational model thing is happening between is this, right? So as long as if I have enough data to train a reasonable unary classifier, I'll be okay. If for instance, if I have a situation where all my events are day and one event was at night and it's all dark and completely screwed up image features, then I'll have problem probably, right?
As well?
So
Or just label faces?
basically we have labeled faces only to start with, and we initially if we have timestamps on the images, we just run a clustering on times to basically come up with IDs for events. Right? Yeah.
I think kind of the next question after Ryan's question is what happens if you obscure a face? So if you take someone's face and just hide it in all the images, will you be able to identify this person still?
Yeah, it then depends upon the relational model. If you have a strong relational model, then it'll basically give you a probability distribution over it, even if you don't have this. Right?
Have you tried anything like this?
We have not. That's a good idea. We should probably try it.
Like pictures where people do these kind of things, your model should work much better than other image sets which have.
That's a good idea. Someone's like doing this, and you can say, all right, I know who you are.
So is there a difference between those two image sets? One was that Gallagher image set, and is there some kind
It
of
might
a
be.
difference?
Yeah, it might be. Again, I need to go back and look at it in detail. Honestly, these are some of the good issues. I think it might be. I should do that.
Are these accuracies assuming that you have 100% accuracy in face patch identification?
Yeah, face patch. It's it's pretty good. Again, it's state of the art, and
Well, they do terribly when you see the back of a head.
Yeah, the pose and all
you
that.
should be able to identify
that.
somebody from the back of the head in lots of cases.
That's an
And so-
interesting.
so you actually
I should try to do that.
It shouldn't be face patch. It should be
like an oval
head patch, and it's now you can't. It's a different identification problem.
No, yeah, that's a.
When
That's
the face
a good
is hidden,
idea.
that's level 2. Level 3 is if you see the face and it says it should, he shouldn't be with her. He shouldn't be with her.
You can read that out as well.
correctly, but she's the wrong one.
Yeah, that's funny.
arbitrary body parts too.
But then
Actually, it can be like a surprise detector.
Probably can, because you'll have a picture of you with your wife, and she shouldn't be with you. She should be.
That's V3.
All right. So the next set of experiments were like, what if we use, these unary classifiers as features? Like, the first thing that I had talked about. Instead of doing this relational inference, what if I have these, context classifiers, but use them as a feature in classification, right? So, using only faces again, around 39%. Like clothing bumps up. If I use the timestamp, some people use the timestamp as a feature, as a context, right? Doesn't do well. Cross inferences again, that what we talked about. So really, if your context classifiers are not that strong, you're pretty much screwed basically, and that's probably not the best way to go about it, right? And that's what it's trying to show. And interestingly, like there is a, so far I had only talked about people event, but I had nothing about people location, right? So in fact, the gain from people location, if I have people event already, is very marginal, because usually location and event are highly correlated. So if I have incorporated event, it's kind of same as having location altogether.
But that changes if you have multiple albums from different people, right? Where the event segmentation is per album, while location you would be able to actually start now having edges across different people's.
Yeah. You have those cases. Yeah.
It sounds very different. So if you're talking about party, right. But if I'm traveling now, then it's going to be
It's different. Yeah. The thing is, it's basically how well can you characterize the event and how much correlation is between events and the location, right? In this data set, unfortunately, there was a very high correlation.
That you have multiple images from the same event. This is not necessarily true. Whereas it is likely to assume that in the same day I won't be in Europe and in North America.
Again, some intricacies of the data sets here probably. The the location and the events occurred together. But then the thing is that.
Well, it's because you chose to. I guess no, you do have the other block.
Yeah.
I didn't see the PLPP block.
Yeah, I mean we tried all possible combinations, and then the thing is the good thing then is that like location labeling is very hard because I'm just looking at the background of images, right? But now if I start incorporating event, that accuracy goes up. So even though it didn't help us with recognizing people, but its accuracy of finding where the location is went up because now. So I mean again it's kind of saying that all of the three classifiers are getting benefited because we can do this bootstrapping of each other, right? And yeah, I mean it's basically accuracy for event label as well and similar results. So again the cool thing is again Bayesian model, again I can do that trick of active learning, right? And that's what it is showing here. The red curve is basically the active learning with cross inference, right? 150 images, if I'm able to label even like around 39 40 images, I pretty much nail the rest of the data set pretty just because of this information flow going around, right? And again there are like 4 different kinds of sampling strategies. All right, so basically pretty much I think the message is it helps sometimes if you can model each of like the relationships between different domains, specifically if they are dependent upon each other, instead of trying to use them as a feature into a cascaded classifier, right? Again, you can imagine doing this thing to other classifiers beyond faces, right? Like mobile scenarios or like a lot of people actually, we are thinking of using it for human behavior modeling, like people do certain, say, their cognitive states based on what they are doing, and often they are also very codependent, so you can exploit that. I'm sure you can do a lot of stuff on health, right? Specifically many of these signals are probably dependent on each other, and instead of using all those signals as a feature, you might want to maybe think about modeling them individually and then trying to model the relationships across. So yeah, so that concludes it. All right.